So, good morning, good afternoon, and good evening. I'd like to welcome you to our webinar on an introduction to the International Irradiation Association's roadmap to an electron beam or X-ray center for industrial applications. I trust everyone's able to hear me and see my slide. I get a thumbs up or an affirmation from somebody. Okay, good. This document offers a high-level overview of the information needed for decisions on whether to invest in an e-beam or X-ray system. It's mainly for people with little prior knowledge of this technology. It was authored on behalf of the e-beam and X-ray working group of the IAEA and with the input of other IAEA members. Financial support was provided by the U.S. Department of Energy's National Nuclear Security Administration, their Office of Radiological Security. This is the outline of what we're going to cover today. First, we'll start with Jörn Meissner. It's going to give an overview of the roadmap. Then Sharon Balt will give us a case study on how the roadmap can actually be used. Evan Thompson of the National Nuclear Security Administration will discuss their interest in accelerator-based sources of radiation. Then Selena Horak of the International Atomic Energy Agency will review their interest in accelerator-based sources of radiation. And then we will have Q&A at the end. As questions arise, please enter them into the Q&A function. The agenda has allotted time for questions at the end. Any questions in the Q&A that are not answered during this time, we will make every effort to get them answered offline and posted. My name is Thomas Kroc. I am the U.S. representative of the IAEA, and I will be moderating this webinar. Our first presenter is Jörn Meissner. He's the CEO of Meissner Consulting. He's one of the primary authors of the document, and he's going to give us a brief overview of the roadmap.
Thank you very much for the introduction, Tom. I'm going to talk about this roadmap and how it developed in the next 12 minutes, just to give you a brief overview on why is it important for you, what can you do with this, and why did we even do this at all. So let's start with the purpose. I mean, many new customers lack an experience of this technology and lack easy access to the information that is needed, what e-beam X-ray can do for their process. They would like to have an unbiased comparison. They would like to find out where to find information that is unbiased, where the key suppliers are sitting, and for that we even have a database on the website, on the IAEA website, and how to perform a feasibility analysis in such a way that at the end you have a bankable business plan for a technology that is new to the users. So if you don't have this information, what we have seen in the past is that their project gets delayed. It does not even get off the ground sometimes. It becomes too expensive for the purpose and it lacks financing, and they spend a lot of time in order to try to find out why this whole thing didn't work the way that they wanted. So what we really need is an easy to follow roadmap without too much technology details, but focusing really on the business part of things. So the purpose is that we enable electron beam and X-ray project developers, the prospective buyers of equipment, the prospective investors. And this is about business plan analysis and feasibility studies, not so much about the technology itself. It shall enable the project developers to find supplier independent information, either in this report, by the links in the report, or on the IAEA website in the supplier database. We are trying not to duplicate the information that is already out there. We're trying to link to that information instead. Now, we had to select some target markets in order to make this a document that is easy to read. So we chose medical device sterilization, which includes combination products, pharmaceutical sterilization, consumer products. So pretty much everything that has a 10 kilogray dose or more. We also looked at phytosanitary treatment for quality control, biosecurity. This is a dose range that is 1 kilogray or less. So typically fruits and vegetables. We also had a food irradiation mine, so that's a dose range in between, mainly for dried fruit and spices, pet food, meat products, currently not the biggest market. Polymer irradiation did play a role, and we were considering, not really looking at in detail, using tray-based conveyors or strand handling systems, such as for wire and cable. Now, are you ready to cut the ribbon on your new Xray facility? Well, let's have a look at your motivation first. Do you want to enlarge the capacity in a growing market, or you want to transition to E-beam X-ray from gamma, for instance, or from ethylene oxide? You want to phase out of chemical process, which especially in the pharmaceutical, in the phytosanitary market is a big driver. And you want to meet the regulatory requirements for biosecurity, sterility, and radioactive material transport, which may be hassle. Or you just want to deal with supply chain issues that you may have with cobalt supplies or other systems. Now, with that in mind, how do you get there? You need to make some decisions. And really the whole thing is a product-based decisions. What is your product? How is it packaged? And what is your dose requirement? Dose requirement typically comes into two ways. I mean, you need a minimum dose for the product, for the process to be effective. And you will get a maximum dose either by regulated processes or because the material cannot handle more. So what you need now is the best fit technology for your dose uniformity ratio and your dose limits. So, but this is the question, does it also fit your budget? If you have a product that just needs surface sterilization, then typically you can deal with a low energy E-beam. You still have to test or experimentally test if the dose uniformity ratio is okay. If it's okay, great. You just chose the lowest cost investment for your product. However, if you go one step further and say this does not meet your requirements for the dose uniformity, you maybe even have small packages at very low density, then you go to medium energy electron beam. Now, this is a fuzzy definition. Medium energy is defined by many people in many different ways. For me, it's from a few hundred keV all the way up to a few MeV, but not exceeding maybe 3 MeV. At least that's my definition. And my definition is not really important, but what it does do for this definition is that defines kind of a CapEx line that if you go higher than 3 MeV, then you will cross a step function in the capital expenditure cost. And that's what I'm actually trying to say. So once you have larger cartons, when you have still low density, you can probably get away with high energy E-beam, let's say 5 to 10 MeV. And if that works for you, great, then you have the best ROI for your process. If, however, you say, well, this also doesn't work for me, you go for high energy X-rays. You can treat pretty much everything with high energy X-rays. However, you're looking at a budget constraints that is 25 million to 50 million in that range. Now, as a summary for this, electron beam, you treat in boxes. You have the best return of investment if it works for the product. X-ray, you can have pellet integrity. You don't need to do any packaging changes. You have a machine source for radiation. You can turn it on and off. You have the best dose uniformity between all the radiation processing methods, and you have a scalable production. You can do a very quick product change because your treatment zone in X-ray is rather small, but you have a very high electricity requirement. And I'll come to that in a moment. So in gamma, I'm just mentioning this for the completeness. Yes, you do have the same thing. You can have gamma irradiators with pellet integrity where you don't have any packaging changes. However, you have to have continuous production because if you don't produce 24/7, your cobalt will decay anywhere. So your operation cost is really based on cobalt decay mainly. It is a very simple operation. You just need to load it and wait. However, you also have a slow product change. So when you have a density change, it takes a while to transition from a low density to high density or vice versa. You have a very low electricity consumption, but you have cobalt decay. That is your major operation cost. And of course, one of the things that is a real issue right now is the transport of cobalt-60. Not so much the availability anymore, but the transport of it is a little bit of a hassle, especially now when the IAEA is producing new guidelines for the transport limits. Just as a recap, E-beam dose uniformity. If you go for E-beam 10 MeV, then you look at densities that go up to 0.3 gram per centimeter cubed. You will have to pay attention to packaging and to the side at the direction of the beam. You even have to pay attention to the packaging inside, and you often have to treat from both sides. The picture on the right side, where my laser pointer is right now, shows you a prime example that I borrowed from the trad people. That if you radiate it from the side where there is a shadow effect, like this tantalum pin on this polymer box, you see this shadow, and you will not reach the dose uniformity that you need. So this is just an example of why E-beam dose uniformity or E-beam dose mapping is going to be a complex thing. It is worth it to do this for business and capacity planning, because modeling provides you an oversight on what you can do. It doesn't give you the validation, but it gives you some very good idea of where you're going to, and you can do your business plan this one. Don't do this just yourself. Get an expert to support you. Trad is out there. There's other people out there, and they can help with dose uniformity testing on this product. Xray, totally different animal. You irradiate typically from the side. You always irradiate from both sides. Dose uniformity is really more in the terms of average density of a pellet. And there's a paper out by Arial and I think IBA and Trad on irradiating apples. So hence high density fruit with very low density air in between. And they have shown that this is actually a product that can be treated as an average homogeneous product when it comes to dose uniformity calculations. Also here, it's worth to do some modeling when you have complex products, and you do need to have a dose map and experimental verification, because one thing in X-ray is very difficult to get good numbers on is the actual production capacity and throughput. There's always some guidelines that you will get from the vendor, but it is with a 25% margin of uncertainty typically. Now, you want to optimize your business case. So select the energy, the lowest energy that fits for your product, because that's going to be the lowest investment cost. So that defines what type of accelerator you need, and you can go then to the IAEA database to find an accelerator manufacturer that fits your needs. Once you have defined the accelerator, that automatically kind of decides on your shielding requirements, decide on the power in order to go for your production capacity. Power is proportional to production capacity. Make sure that your machine, your investment fits your business needs for the next 5 to 10 years. Keep in mind that it's not just the accelerator. You also need to have the building. You need to have mechanical, electric, and plumbing systems. And you need a product handling system. And you need to consider that the utility cost for an accelerator is definitely something to be considered in the operation cost. Just for pi times thumb rule, the beam power that you choose to have, multiply that by 3, and then you have roughly the facility connected load that you will need for your new facility. If you go for X-ray instead of E-beam, you have another big capital expenditure step, and your production capacity is taking a step in the other direction down. If you say, well, all this is really risky and I don't want to take that risk, you can ask suppliers for turnkey projects. But please consider that for a turnkey risk to be taken by a vendor, they also need to have a margin. So you pay them to take the risk, and really you pay them to do that. You can take that risk yourself, probably cheaper, and you are in this business of your processes. You have taken risks in a similar order of magnitude for your existing process. So it is really a question on where you want to go. Sell the risk or keep it. Carefully review the product needs with experts so that you make the good choice about energy and power and packaging, and consider risk mitigation by experts rather than buying turnkey. Now, the main operation cost in any accelerator facility is going to be staff and utilities. You will have a certification constraint that sometimes you need to have a certain certificate in order to actually start the production. You will start most likely ramping up your product. You may not ramp up as fast as you want. You may actually run into small batches or partial batches that reduce your efficiency. And last but not least, but your customers may actually say, well, we do not want to repackage. So this is something to consider in the very early phase of the feasibility study to make sure that the packaging that you assume is compatible with your customer requirements. Don't forget that community acceptance for a radiation facility may play into your schedule if this comes out during the permitting phase, and please also consider that utility outages may play a role in your uninterrupted process. And with this, I would just like to pass over to the next person, and I thank you very much for listening.
Okay, thank you very much, Jörn. So based on your experience, how broadly geographically is E-beam and X-ray these days?
Well, you find it in all continents where you have a good electricity supply. So, I mean, Asia, Southeast Asia, Australia, you find it in North America, for sure. You find it in South America, of course, Europe. A little bit scarce on the African continent. But I think that we will later on hear how that is going to change from Cecilia.
Okay. And of course, the question always is, how much does it actually cost?
Yeah, I think that you can get away with about 1 million for the lowest cost system, and for a full power X-ray system, you can run into the 50 million range. And anything in between is possible, but I have not seen an E-beam plant that is a production E-beam plant, let's say for medical device sterilization, that is less than 15, 20 million in these days. Probably more, 25. I mean, 10 million.
But that includes, is that the whole building and bunker and all that?
Yes. I'm always talking about the complete project because, I mean, this is about business, right? So I'm not selling any equipment. I'm just advising customers on the overall feasibility of the complete business process, from starting this whole thing on a green field until the product comes in through the door and rolls out of the door. So really getting everything ready for that first truck of product to arrive. And that's kind of the cost that I'm considering in this case.
Okay, great. Well, thank you so much. And thanks for all your work on this roadmap too. Next up, we will hear from Jörn Balt. She's the managing director of HEPRO-CATE, an irradiation facility in Cape Town, South Africa. And she's going to show us how the roadmap might be used.
Thank you very much to you, Tom, and organizers of this webinar, to describe the journey that we took at HEPRO relating to the potential use of E-beam X-ray here in South Africa. The question was, why on earth would we want to have E-beam X-ray when for 40 years HEPRO has been successfully operating a gamma irradiator, which irradiates foodstuffs, medical devices, pharmaceuticals, packaging, and cosmetics? Well, the fruit industry in South Africa, together with HEPRO, investigated the use of phytosanitary irradiation as a mitigation method. And after many seasons of testing the suitability of gamma technology, the industry was ready to use this technology for their purposes. The next step was to consider whether to continue using gamma irradiation technology, but due to the configuration of this current facility at HEPRO, this allows the possibility of processing high cube pellets. The volumes, as well as the added worldwide shortage of cobalt-60, gave HEPRO cause to explore alternate technologies, and so began our journey looking at the possibility of E-beam X-ray. At this point, having no prior knowledge of E-beam X-ray and no roadmap as yet, we gathered the information from source, and we owe significant gratitude to our partners like Ariel, Mevix, and IBA for their patient guidance in answering our endless questions. This roadmap closely resembles our journey. Key technical concerns arose, and I'll address a few. These are addressed in section 3.5 of the roadmap, as well as in the flowchart in figure 3.1.1. The first and most important for us was recognizing that the power supply, recognizing that constant energy is a crucial factor for the successful operation of E-beam X-ray facilities. The idea initially seemed a bit unrealistic, and given our unstable supply in this country, this was a big consideration for using this alternate technology, which could operate in the context of South Africa's energy challenges. Just to give you an idea, South Africa's daily power outages were up to 14 hours, which forced us to consider lithium batteries, solar panels, generators, inverters. So essentially just having enough power was our main concern. Sustainability was not really an issue for us at the time. It was just an added benefit. Then we looked at what kind of power we would need, as well as the processing energy 5, 7, or 10, or 10, shall I say, depending on what products we were going to do. Of course, long-term use, gamma users had concerns about the performance. The facility layout as well was an issue, as we needed to see whether it was E-beam and X-ray in the one facility, reducing the space and capex requirements. Cold chain logistics were an important issue, as the facility was due to be positioned close to cold storage for streamlined logistics in the treatments of products like fruit. Now, legislation, I think Jörn quickly referred to it. Legislation plays a critical role determining whether products could be sold in other countries. Our question was, will the regulations facilitate the trade of irradiated foodstuffs? We then went on to identify potential customers, which was really the essence of the whole exercise, as we were not only going to be doing phytosanitary treatments, so we decided to do as well medical devices and other related industries, which proved to be the most sustainable. Information such as the geographical spread of the customers, where export logistics had to be factored in, including ports, the timing, and the seasonal availability. Temperature sensitivity for those products was an issue, and the global transport events like shipping delays and route disruptions had major impacts. During COVID and post-COVID period, it was impossible to easily find containers to transport goods. This helped the air freight of irradiated fruit to find a foothold in the market. International codes and timelines. Timelines are very important. Delays are of prime concern, where you would have red tape, export approvals, etc., causing certain delays. In this country, we also considered whether it should be management, should be private or government controlled. That depends on the area which you work in. And different countries have different dose of energy requirements. And as a result, you could find delays in those areas as well. In conclusion, I would say the greatest challenge for us here in South Africa was the power stability. Everything hinged on reliable energy. And while sustainability was a minor focus for us, the investor confidence based on the economy, political environment, technical feasibility, market alignment, and legislative readiness shaped the foundation of this venture. Thank you for your attention.
Okay, thank you, Jörn. So where are you in this process?
We have completed our feasibility study, and the process has now been parked since the investors are hesitant to invest in such a huge project at this point, which is the question I was asked, whether it should be a government project in this country or should it be a private project. Potentially that would now become a government project. It opens new markets for the government.
Okay. Well, thank you very much. That was a very interesting analysis. Next up is Evan Thompson. He's with the National Nuclear Security Administration in the US. As mentioned earlier, the NNSA provided funding for the development of this roadmap. Evan doesn't have a proposal or a presentation. We're going to do this as a Q&A thing. So welcome, Evan. It's great to have you.
Thanks, Tom. Yeah, thanks for having me, and thanks to IAEA for taking on this a great project to make the roadmap. I think it's been a huge success so far.
Yeah. So what E-beam applications show the most promise as growth markets that can stimulate and sustain domestic manufacturing of E-beam systems?
That's a great question. So I definitely believe that, broadly speaking, we're going to see a lot of demand for both radiation treatment of phytosanitary needs for foods, pet food, all of that good stuff. But of course, the big one is always going to continue to be medical device sterilization. I think that's something we see year over year growth in. And, you know, as we've already talked around a lot already in the first two presentations, you know, we saw where the pain points can be in that system during COVID, for example, and being able to support that with growth in E-beam and X-ray development is going to be key. That being said, I think there are a lot of really sort of new application spaces that we're going to see a lot more demand in as well, that may tax existing ability to meet it. And those are things like sterile insect technique, the things we need for agriculture security, protecting our crops and our livestock. And then, of course, things like environmental remediation. We're seeing a lot of interest in addressing PFAS and those forever chemicals. And right now, we don't have a good way of addressing them except through really other chemicals. But I think we're seeing great strides in E-beam, for example, being something that can address them. So all those things together, I think, are growing markets, and some of them are emerging markets that we're going to see a lot more demand for.
Okay, thank you. So Jörn touched on this a bit ago, that we have a bit of a terminology problem, but what will the development of mid-energy range compact systems be key to expanding the industrial radiation market?
I definitely think so. And this is definitely something that we are very interested in as the NNSA and ORS. And I think we're seeing a lot more interest in industry and in sort of meeting this need across all of the applications that I just mentioned. So we have, I think, a lot of really good solutions on the high end there, you know, the 7 to 10 MeV electron beams and being able to address those in large sterilization facilities. And then on the low end, we also have a lot of good solutions. The, you know, 1 or less MeV energy ranges there for things like polymer modification and hardening of materials. Where we have that gap, I think, and where we need to see more is in that mid-energy range. And I think really the sweet spot there is maybe around 4 MeV, 3 or 4. And we're looking at how we can get more of those into the market. I think that will fill a nice gap that we have there and will answer a lot of the questions to meet the need for some of these emerging applications, absolutely, and even some of the growing ones. I think this is something there we could see a lot of interest in medical device sterilization and the capability to bring some of it in-house to meet that need going forward. We just need to find the technical requirements and what the actual solution is there. But I think it's really the sort of future of E-beam, so to speak.
Okay. I assume for the most part you're talking about US market in that, but you've also got some extensive international experience, right? So how what's your international perspective on this?
Absolutely. So, I mean, obviously, I am a federal government employee of the United States. So I'm first and foremost a public servant for the U.S. people. But we are doing a lot of things to encourage the adoption of these internationally. We've spent years conducting sort of regional workshops to promote these technologies in every region of the world at this point. We've done one in Latin America, we've done one in Europe, with Africa, we've done one in Asia, and so we've done the full circle of the globe to sort of promote these technologies and encourage their adoption of them. And we're also doing a lot in the United States as well. Of course, we want to promote U.S. accelerator manufacturers. We have some terrific ones there, but we are doing things that I think will improve the accelerator industry wholesale around the globe. We're working with companies to improve the affordability and robustness and the effectiveness of accelerator components, for example, making klystrons a little bit better, working on the development of solid state modulators. And that's the kind of thing where I think, you know, a rising tide lifts all ships kind of thing. I think we'll see benefits not just for U.S. industries, although that is a key part of it for us, but for everybody that has a stake in accelerator development and accelerator use.
Okay, thank you. What are the most needed skills for growing domestic e-beam and international e-beam manufacturing market?
That's a great question. I mean, I think this is something where we've seen a lot of demand for a very, very broad set of skill sets. So obviously we are talking about sort of high voltage engineering here. And I think that's a key one, being able to have the people who are knowledgeable in there and have the vocational skill set in order to maintain these devices. I think we have a lot of really good opportunities to build them, but we're also going to be competing against some of these other growing industries, including the nuclear energy sector. They're going to be asking for a lot of the same skill sets in terms of engineering and development. So I think we really need to be focusing and working with our partners across industry and across academia to make sure that we are building that huge range, right? We do need a lot of really high technical, high engineering degreed individuals, but we do need to make sure that there are those vocational pathways as well, the welders, the casters, and the people that are going to be really putting all of these together and sustaining these devices around the world. I mean, we're only going to be as good as our ability to sustain these technologies. If we buy a bunch of them and have no way to repair them, we're going to be setting ourselves up for failure. So I think making sure we have those connections, those pathways up front is going to be absolutely critical to ensuring the success of all of the industries wrapped up in this.
Okay. Any recent electron beam system design modifications that appear to show the most promise for reducing capitalization costs or improving operational cost efficiency? Is there anything on the horizon?
Sure. I mean, and I will say that, you know, we have a lot of great partners that are working on how to make things better all the time. So I think we're going to be seeing a lot of great things coming down the pipe in the next couple of years. One thing we're really interested in, and I you know, name checked it a little bit earlier, is solid state power sources. I think that's something where there's a lot of promise there. It does have a little bit of a higher capex cost, but when we're talking about the effectiveness of these technologies, these components, and how much more robust they are than the sort of average or typical klystron that has been used and has been the workhorse in this industry for many, many years now, I think you really start seeing that really pay for itself over time. You don't have to replace them as often. They need less sort of hand holding and using them. So I think this is somewhere where we're going to be examining how we can, you know, get those into the market. And I know I've talked to industry partners that are doing the same thing. So I think we're all sort of looking in the same direction. It's just figuring out how to get there in the most cost-effective way possible without upsetting too many of the ongoing operations.
Okay. Is e-beam the best technology to reduce health risk from the proliferation of non-biodegradable synthetics in natural systems?
So I don't know if it's the absolute best, but it's definitely a great one. So, you know, I did already mention that we are seeing a lot of great work being done, in particular at the national laboratories around the country in addressing PFAS, that forever chemical, as you hear about it in the news. And we're seeing a lot of really great strides there. You know, these e-beams use high energy electrons to generate reactive species that break down those strong carbon fluorine bonds. And that's something that we haven't been able to do except with other chemicals in the past. And we don't want to address the chemical problem by adding more chemicals to the mix. This is a way that we can treat water, treat soil, and really help the environment and help the productivity of the United States through a process that won't add more chemicals to the system. It's a really exciting stride that we've seen at Fermi Lab and Jefferson Laboratories, and we're seeing some uptake in private industry as well, and we're excited to see where it goes. I think this is one of those emerging areas that's going to have a lot of impact in the future.
Okay. Well, thank you very much, Evan. If you want to, you had one slide you wanted to show real quick before you
Yeah, if you don't mind, Tom, and thanks. This is a great conversation, and I think we're excited to keep this going. I wanted to just flag that we are having an event. Can you see that, Tom? Is that coming up okay?
Yes, yes.
So we are having, if you are familiar with our industry day that we had in 2023, we are having another one next month, June 10th to 11th in Arlington, Virginia, just across the river from Washington, D.C. This is an invitation-only event, but we can be persuaded to part with some more invitations. If this is something that you have more interest in and you want to be part of this discussion, reach out to orsinfo@nnsa.doe.gov, and we'll talk about adding you to that list, because we want to have as many voices there as we can to talk about the opportunities, the successes, and the path forward for e-beams and X-rays across the world. So thanks, Tom, and happy to take more questions a little later if needed.
Okay, thank you so much. Finally, we have Selena Horak of the International Atomic Energy Agency. She is the section head of radioisotope products and radiation technology, and she's going to explain the IAEA's interest in the roadmap.
Thank you very much, Tom. I hope that you can see well the presentation.
Yes.
If so, well, I'm going to talk about, of course, the IAEA role in this radiation technology, but also, of course, why we are interested in this roadmap, because it's fully aligned with the programmatic activity the IAEA has. So moving into let me have a look if moving, yeah. So, and when I was talking about how it is aligned to our programmatic activities, part of our mandate is the medium-term strategy. It has been already defined that we have to continue building capabilities in the member state on the nuclear science competence. So, and this means that the radiation technology can be safe, useful, sustainable, and in both areas, on those countries that are already chose radiation technology using radioactive sources, that, well, it has to continue being safe, and secure. And those that would like to continue using that, well, we will also try to follow up with them on this security and safety aspect. And of course, we are very interested in this transition to the machine-based technology, in the use as accelerator for, well, all the aspects that this technology can contribute. And, well, what can IAEA do in this aspect? We are supporting all the different kind of technology, from the, as I mentioned, from the radioactive sources, gamma rays, and also in the case of machine-based technology, electron beam and X-ray. And we are supporting in those aspects that the member states are showing some interest and showing some demand. And of course, developing more guideline and more training on the radiation sources, on the quality management, both for all the quality management system, but also for the dosimetry system, our control process, and also implementing some intercooperation exercise on the dosimetry system. It has been implemented globally, this kind of intercooperation exercise, and was very successful. Also providing some guideline, training program, and also, well, complementing with our colleagues here in the Department of Nuclear Safety for, well, supporting those countries that are requiring to enhance the framework, the safety and security framework, but also in the operation as well of this kind of technology. So, and also not only on the radiation technology side, on the machine side, but also in the application, the use of this technology, from going from the very low doses to high doses is part of our also mandate, to support the member state in developing the capability through different mechanisms in being able to use this technology, and especially now the machine-based radiation technology, for being applied for the different kind of purposes, from, as has been mentioned before, SIT or, well, phytosanitary, sanitary treatment for the food and agri-food, in the case of raw material, medical devices, tissue banking, the tissue allograft product, labware that is being treated also by this technology, cosmetic, and also, of course, those applications that are on more high doses, such as when we are expecting some modification application and functionalization of polymers, or for environmental application, and also all these aspects, as has been mentioned before, on the PFAS, and also flue gases, greenhouse gases, and others. And also something that we also been discussing recently with colleagues in PAHO, is about also the replacement of the cesium irradiator, self-contained irradiator by Xray. That this is something that we are also working together with colleagues in the Ministry of Health in these regions. And just for giving an overview of what is the status on the e-beam of our member state, we are having very few member states that are using this technology, the e-beam technology. And we are having, as Ivan has said, a high demand from them. They are really interested in this technology because it provides a lot of benefit that has been already mentioned. As you can see here, only 40 member states from the 180 are having this technology. So this is quite low number, and our expectation is to try to increase this number in the near future. So what can I do more in this direction now on how to implement the e-beam technology in our member state? Well, as everyone knows, we are organizing different kind of meeting, strategic meeting to try to get the best solution for our member state, sharing the last advances, and also as this roadmap is showing, how is the direction that all the member states should follow to really understand how to apply or implement the technology. And this is absolutely wonderful because it's absolutely what we are looking to support our member state. And the idea is that also we can make the technology more convenient and adapt more tailored to the application that the member states are looking. And this is what we are now developing through what is called the flagship initiative, the IAEA flagship initiative, such as the no-tech plastic, atom for food, Zodiac, and atom for climate. That is not a real initiative, but it's like a global issue in which we are contributing as well. In the case of no-tech, there is a lot of benefit of this technology because we can treat in a continuous process bulk plastic waste, but also synthesize some bio-based plastic from biomass. In the case of atom for food, everyone may know phytosanitary and sanitary application, additionally to the SIT. In the case of Zodiac, we will start working on the developing of some vaccine as well. And for atom for climate, of course, we can treat we are impulsing a lot of R&D, but also more apply a mature technology on the environmental application for the gases, liquid, and solid. And now moving into the second point, the transportable e-beam for training and promotion on-site demonstration. We are also pleased to receive the support from NNSA on this area because it was amazing. And we will receive by September, during the general conference, this transportable electron beam that is a 700 keV, self-contained. It will have all the accessory for treating gases, liquid, cables, film, and also it will have a simple conveyor to treat it, bulk purchase, such as, for example, in the case of the vaccine, that we will collaborate with our team here in health, in the animal health here in Salvador. So this transportable e-beam will be located in Salvador laboratory, and we will have laboratory also there. This is something quite innovative because up to now, IAEA doesn't have laboratory specifically in this radiation processing application. And the idea is not to replace what many institutions are already doing, but just try to give the basic knowledge on the security aspect, safety aspect, on the operational aspect, the preliminary maintenance of this kind of equipment, part of the electronic that is being required to be more, sustainable in time, especially because many developing countries are facing the issue of when they are having this kind of equipment, if they are not having the qualified and very skilled staff, they are, well, struggling in having the machine maybe broken for a very long time. Of course, the technical service is not being replaced because this is the supplier who has to provide that, but at least the basic maintenance and repairment can be done. And this is our main objective here. And well, this is some, application that will be possible to do with this transportable beam. We can treat, as I mentioned, flue gases, different kind of gases, the wastewater, we will have the accessory for water, for liquid and sludge, and also for other kind of, the bulk irradiation. And also there is a second accessory that is like the transportable beam will be mounted in a 40-feet standard container, and there is another 20-feet container that will have all the accessories for treating wires, cables, and also the film. So it's very, very, very complete, the package that we will have here in Sabledorf. We are very happy on that. And in the third point is another strategy that we have been working since last year, together with our colleague Von Suhan, who has retired from the agency, unfortunately in last March, but we work a lot and we will continue working on this direction, is to make electron beam technology accessible to our member state. But this is not just the purchase, the bulk purchase, is the whole process. And here, if with this roadmap, make really a difference, a significant difference. That's why we really appreciate that this document can support the member state in understanding better this roadmap, this long way that sometimes is very complicated for them to understand better what are the steps that they have to follow. But the idea is to having at least two kinds of specification in the first stage that can make the life simple for our member state. And with this generic specification, also the supplier can have more easy way to developing. The design stage will be already ready, and they can, if everything goes well, lowering a bit the price if we are buying in the bulk purchase. And that's why we are considering also long-term agreement for this kind of procurement. So this is under developing, and the strategy is going well, and we are in the developing all the additional to the concept note that was the preliminary idea, is also all the term of reference for the approval internally here in the IAEA. And these are the two main specifications that has been developed last year during a technical meeting with many of the suppliers of the machines. One is what has been called like a baby project, and the second one is the star project. The baby project is mostly for replacement, let's say the gamma cell style, the self-contained irradiator based on gamma. Well, we will be able to replace it by this kind of e-beam technology. And then the big project that it will be for those that has already the experience and they want to do this transition into the machine-based technology. Well, that is the reason why we are having this second option. And as I mentioned before, we want to.
So Selena.
Yes.
So I think this maybe is a good stopping point, if you don't mind.
Sure, please.
We're at the point of the end of what was allotted for you. So I want to thank you all for your informative presentations. We've received an overview of the roadmap itself and seen an example of how it can be used to analyze your situation. We've heard a couple of viewpoints on why this is important on a national for the US and an international level. And now we're going to put up the slide for how to access the roadmap, and then we'll get to your questions. So if you have questions, please put them into the Q&A, and we will start working on that. So the QR code there has a link to the roadmap itself. if you're interested in joining the IIA to help support this type of work in the future, you can go to IIAglobal.com and for our website, and there's information there on how to join, or you can email us at info@IIAglobal.com. So there's a Selena, do you have a link to the projects that you've mentioned in your presentation?
Yes, we have some, but yes, we are in progress in some of them. Yes, but we can provide as soon as we can everything ready. Yes.
Okay. We have a comment here. Says, I am aware of the ongoing discussions about global cobalt supply shortages, particularly given the geopolitical situation in Russia, which I believe was a significant supplier. In our company, which relies on a sterilization provider to sterilize our biopharmaceutical equipment, there is some uncertainty. We are hearing conflicting reports from some sterilization providers who claim that cobalt supply issues are unfounded. Can you clarify the current situation? Are we genuinely experiencing a shift towards X-ray sterilization? Jörn, I wonder if you're maybe the best person to respond to that.
Yeah, there are two aspects. There's actually two aspects to that answer. Number one, shift towards X-ray sterilization. I think there's many reasons why people shift to X-ray sterilization, and not all of them are based on the cobalt supply chain. I believe that I've seen that Martin Kompen is part of the attendees, and he would probably be a better person to answer on the actual cobalt supply situation. I've heard the same reports that the actual cobalt shortage is not really a real issue anymore. It's more the transportation part that is the big issue.
Okay. Martin, are you able? Yeah, go ahead.
Thomas, can you hear me? Yeah, okay, yeah. So, slightly unprepared. I actually responded to Emmanuel directly, and I've offered to send him an update by email. But yeah, in summary, there was a tightness of supply between 2018 and 2024, cobalt supply. That was brought about by a number of factors. One was an increase in demand, and that was linked to the COVID-19 pandemic. And one was due to reactors closing either permanently or temporarily. So, for example, one of the reactors, actually several of the reactors over time in Russia closed down permanently, but new ones in Russia have been reopened. The reactor in Canada closed for refurbishment, and refurbishment is quite typical during the working life of a reactor. That was a reactor in Argentina that has now been through refurbishment and has reopened and is producing cobalt again. And then there's a number of reactors in Canada that were also going through refurbishment programs. So the Bruce Power reactors, they're in the middle of a refurbishment program. Some of those reactors have reopened. Some of those will reopen over the next 5 or 6 years. And then one of the advantages of refurbishment is that you can modify reactors of a certain type to enable cobalt production. So a number of those reactors in Canada are operated by OPG. They're going through a refurbishment and modification process, so they will also be adding to the production of cobalt. And in fact, I think one of those reactors now has started production. So in the short to medium term, a lot of work and a lot of investment has been done to maintain and increase cobalt production. In the longer term, there's a different reactor type which is being modified to enable cobalt production as well. So that's really scalable because it's the most common reactor type that's used. So in summary, as of last year, the largest cobalt supplier was able to meet all of the demand. Work continues to increase cobalt production to enable demand for the increasing sterilization need to be met, and that's just within Canada and to a lesser extent in Russia. In India, they're talking about doubling the production of cobalt, and China continues to manufacture reliably. So I think there was a tightness that's now over. We're going to see a period of demand being able to met and to be continue to meet, and then I think probably within the next 10 years we'll be back to a situation where there's surplus. Hope that's helpful.
Okay, thank you. So another question is, what will be the forecasting growth of E-beam and X-ray for the next 10-year time frame? That's kind of hard to predict because from what I hear, kind of second and third hand, a number of E-beam facilities are being done privately, if you will. They're not contract facilities, but they're in-house systems and that. In terms of X-ray, I know that the bioprocess industry, which makes single-use systems for the manufacture of pharmaceuticals and vaccines, they did a lot of work in socializing the regulators, both in the US and in Europe and in Japan, with the potential of switching from cobalt to X-ray for their systems. And that went quite well. So there are a number of moving pieces, but without being able to give you a percentage, I do think that it is a growing market. I don't know if maybe Evan has a thought on that.
Probably not a better one than you, Tom, right? I mean, I think it's a little bit of looking into crystal balls and reading tea leaves. I think all the things you mentioned are correct, right? I mean, we're seeing growth across the board. I have heard that in general, right? I mean, one of the sort of service providers likes to say that we work with that there's over the next 10 years a 150 sort of facility shortage, whether that's gamma or E-beam. We're seeing year over year, somewhere between 7 and 10% growth just in the medical device sterilization, right? So that's even without figuring in the growing demand for, phytosanitary, water treatment, some of the cable cross-linking, waste valorization, plastic upcycling, and SIT, which we see as another growth industry. So in terms of growth, what percentage of all of those things is going to break one way or another, whether it's going to go to gamma, E-beam, X-ray, or ethylene oxide, it's difficult to say. I know we have been doing what we can to make sure that people are comfortable in the moving towards E-beam. We're working through Team Nablo, for example, with many of the medical device creators and manufacturers to show that there are comparable effects with their plastics and polymers, that they can use them for both E-beam or gamma. So hopefully with that in mind, we do see that sort of shift there, and that it goes from 5% of the total irradiation and sterilization industry to 10, 15, that kind of thing. But it's difficult to say. I think there's a lot of competing factors there.
Okay. And Selena, since I cut you off there, I'll give you the last question. What is the lowest operating voltage for that mobile IAEA E-beam system to use for testing products?
Can you say again? What is the lower? Sorry?
Yeah, what is the lowest operating voltage for that mobile system?
It's from 0 to 28 milliampere and 20 kilowatts.
What about the
More or
voltage?
less. Yeah, I'm thinking about, I don't remember now. I was looking into that. I can share with you later on. Yes.
Okay.
Yeah.
So as I said earlier, any unanswered questions, we will do our best to get answers offline. and post them when the video is posted in a week or two. So I thank you all for your attendance, and look forward to working with all of you again in the future. So thank you very much.